Have you begun using Kamal to deploy your web apps, but miss having review apps created for you automatically like other services do? You don't have to miss out. Keep watching to begin learning how. I'm a huge fan of Kamal for deploying my web applications. I've been updating my personal projects to use Kamal for deployments, and I couldn't be happier with how smooth it's been for me to migrate to better hardware for less money. However, I admit that there are plenty of things that I miss from the old way of deploying applications on a platform as a service like Heroku or Render. Particularly, one thing that I miss quite a bit are review apps. A review app is a temporary environment based from a branch or pull request that's automatically provisioned with your application's infrastructure and allows you to test changes before merging them into your main branch. After migrating some applications to deploy with Kamal, I really missed having a review app for testing new features when opening a pull request. But using Kamal for deployments doesn't mean we get to miss out on review apps forever. Using a couple of tools, we can recreate the automatic provisioning and deployment of a web app for preview purposes. In this and future videos, I'll go through a process I set up for one of my projects that uses Kamal for deployments, where opening a pull request creates the infrastructure needed to run my app, uses Kamal to deploy the application, keeps it up to date as the branch gets updated, and cleans everything up once I merge or close the pull request. This entire sequence replicates what Heroku and similar services do to set up review apps with the benefit of using your preferred systems. The first video in this series will show you how to automatically provision servers on the cloud when opening a pull request on GitHub, and a future video will go through the process of deploying a web application to the provisioned server using Kamal. Let's get started with part 1. For this series, I'll use one of my projects called TeamYap. TeamYap is a Ruby on Rails application deployed on a Hetzner Cloud server with Kamal. The application architecture is straightforward, consisting of a single server running the web application and a worker process for asynchronous jobs, along with a PostgreSQL database and Redis on the same server instance. My Hetzner Cloud environment also has a firewall set up to only allow HTTP and SSH connections to the server. I want to replicate this environment to deploy my application's code from a given branch anytime I open a pull request on GitHub, where the TeamYap code lives, and I'd like to automate the process entirely. I can do this with a couple of tools that I'm already using. I'll use Terraform for provisioning new servers on Hetzner Cloud. I'll continue using Kamal for deploying the application using the branch's code. And I'll use GitHub Actions to trigger workflows based on some pull request events in my repository. This video will cover the automated cloud infrastructure provisioning using Terraform and GitHub Actions. And the next video will cover how to deploy the application to the newly provisioned server using Kamal. Make sure to subscribe to this channel so you don't miss the follow-up. Before jumping into creating a Terraform project and setting it up on GitHub Actions, there are a few prerequisites to handle on the Hetzner Cloud account. To connect Terraform with your Hetzner Cloud account, you'll need an API token. You can generate one by logging into the Hetzner Cloud console, going to the project where you'll provision your servers, then visiting the security page, and going to the API token section. I'll generate a new token, and it needs a description, which I'll call Terraform Review App Provisioning, and also give it read and write permissions, so make sure to check that option. After creating the token, remember to save it in a secure location as it's only shown once after generation. You'll also need to set up SSH keys on the Hetzner Cloud project to set up on all new provisioned servers. This step will allow you to log into any server for debugging any issues when using a review app. You can add a public SSH key on the Hetzner Cloud console by once again going to your project, then going to security, and going to the SSH keys section under the security page in the Hetzner Cloud project. I'll set up a personal key here by copying and pasting my system's public SSH key and give it a descriptive name like review app deploy key. And while I could set it up as a default key for all new servers created in the project, I'll manually specify the SSH key when provisioning servers using Terraform, so I'll leave this unchecked. One last thing I'll do here is create a new firewall on the project. All of the review app servers can share the same firewall rules on Hetzner Cloud to allow HTTP and SSH connectivity without creating new ones for each individual server. You can set up the firewall on the Hetzner Cloud project and selecting firewalls. I'll create a new firewall here. And at a minimum, I'll allow inbound traffic only on the following ports for any IPv4 and IPv6 requests. So I'll leave this default of the port 22, which is for SSH connections. I'll add a new firewall port to allow port 80. And I'll add a new rule as well to allow port 443. I'll allow all outbound traffic for this firewall. I won't apply it to any resources yet because I don't have any labels. I'll leave it blank. And at the bottom, I'll set a name for this firewall and call it Review App Firewall. With the prerequisites done on Hetzner Cloud, the first step to do here is to begin defining the infrastructure we want to provision using Terraform. In a previous video on this channel called Rails Deployments Made Easy with Terraform and Kamal, I covered the entire process of spinning up a server on Hetzner Cloud using Terraform, so I won't go into too much detail in setting up the Terraform project here. If you're new to Terraform, I encourage you to check out that video first since it covers everything you'll need to know. To make the whole review app generation process simpler for this example, I'm going to store the Terraform scripts in the Rails repository so I don't have to deal with pulling these in from an external source. I'll start by creating a directory in my repository called infrastructure. And the first file I'll create inside that new directory is the main configuration file, which is main.tf. I'll begin setting up this file by defining the Hetzner Cloud provider for Terraform in the main Terraform block and setting the required providers section, starting with hcloud. This requires a map with the source, which is Hetzner Cloud /hcloud. And I'll also set the version, which is 1.49.1, which is the latest as of the recording of this video. I'll also create a block for the provider, which is provider hcloud. And the Hetzner Cloud provider requires an API token to provision resources in your account, which I can set here or in the hcloud token environment variable. I plan to set up the API token as a secret later when setting up the GitHub Actions workflow so I can then use it as an environment variable. So I'll leave this block empty since I don't need to configure anything else. Next up, I want to set up two data sources that I need to refer to when defining the server resource in the script. The first data source is the hcloud SSH key data source to get the SSH key I set up in my Hetzner Cloud account. I'll call this data source review app SSH key, and I'll configure it to look it up by name, which is review app deploy key. The other data source I need is the hcloud firewall data source for the firewall that all the review apps will share. I'll call this data source review app firewall, and I'll also look it up by name, which I set as review app firewall. For this example, I only need to spin up a cloud server for each review app when opening a pull request. So I'll define the resource called hcloud server. I'll give it an ID of review app server and begin configuring it. The server I plan to use for the review apps is the CPX11 type, which is a 2 vCPU server with 2 gigs of RAM, more than enough for my needs. So I'll set up the server type using this value, which is CPX11, using lowercase letters. The servers will be located in the Ashburn, Virginia data center, which I can define in location and referring to it with Ash, which means that Ashburn, Virginia location. And I'll also spin up the servers using the latest LTS version of Ubuntu. So I'll set the image called Ubuntu 24.04, again in lowercase letters. Now, one important required setting for this resource is the name, which refers to the server host name. Each host in a Hetzner Cloud project must have a unique name, so when running the provisioning step, we'll need to ensure that we use a unique value here, so I cannot hardcode it. I'll use a variable that I can modify through the GitHub Actions workflow later, so I'll set this up with var to indicate that it's a variable, and call the variable server name. The last two settings I'll have for these servers are the SSH keys to set the key I added on my Hetzner Cloud account, and the firewall IDs for the firewall I prepared beforehand. Both of these settings require a list, and I'll use the data sources I defined earlier here as their respective values. So data.hcloud SSH key, and the identifier, which is review app SSH key, and the ID that we retrieve from Hetzner Cloud. And for the firewall, it'll be similar. So data.hcloud firewall review app firewall.id. I'm done setting up my Terraform script here, but I still need to declare the server name variable so Terraform knows about it. I'll create a new file under the infrastructure directory called variables.tf. And here I'll set the variable declaration using the variable block and the name of the variable, which I specified as server name. And for the configuration, I'll specify that the type is a string value. So that's all I need to do here. Before going any further, let me test this initial pass of the server provisioning. I'll first initialize the project by going into the infrastructure directory and then run terraform init from the command line. This command will pull down the Hetzner Cloud provider and get everything ready for us in this project. Next, I'll run terraform plan to make sure that I have a valid API token and that Terraform can retrieve the SSH key and the firewall data sources. I'll need to set the API token, so I'll set it using the hcloud token environment variable, and also use the var command line option to set the value of the server name variable, which I can do by setting the name of the variable as a key, which is server name, and equal the value, which I'll set as review app server test. If everything is set up correctly, I should see the execution plan for this server. I'll go ahead and apply these changes to double check that the variable is working as expected and a server gets spun up by using Terraform apply with the same environment variable and command line option. After confirming and if everything is correct, we'll have a brand new server created on Hetzner Cloud in under a minute. If I go to my Hetzner Cloud console and go to the server section, I'll see that the server is in place and ready to use. Now that I know that the server provisioning is working as expected, the last thing I'll do is set up an output value to retrieve the new server's IP address. We'll need this later on in the GitHub Actions workflow to know where to deploy and access the review application. Under infrastructure, I'll create a new file called output.tf, and I'll declare the output value using the output block and declare the output value for the server's IPv4 address. I'll call this output IPv4 address, and for its value, I'll need the reference to the resource starting with the type, which is hcloud server, the identifier I gave it, which is review app server, and the data attribute I want, which is IPv4 address. When I save this file and I rerun the Terraform apply command, it won't provision a server since we already have it in our local state from the previous Terraform apply command, but it'll show the IP address for the new server to have it available for use later. So everything looks like it's working as expected, so I'll clean things up by tearing down the test server using Terraform destroy. I just mentioned Terraform state when running Terraform apply. Running the Terraform script locally works fine as a test, but since my plan is to use this Terraform script on GitHub Actions, we can't store our state locally since it'll be lost every time we run this workflow. Not having the state available means that we won't know whether the Hetzner Cloud server for the review app already exists, and the workflow will always try to create new infrastructure when updating a pull request branch, or not shut it down and tear down any existing servers when closing a pull request. GitHub Actions does allow caching files and directories through the cache action, but this approach isn't ideal because cache entries are deleted if they're not accessed in a certain amount of time, and we really don't know if the cache is going to be there or not, so it's not a reliable way of doing it. We'll need a more durable and easy to access place to store the state, and that's where Terraform's backends come into play. A backend handles where Terraform stores its state, and the setting helps us set the state somewhere that any system with access to that backend store can have the latest information of the managed infrastructure, which is what we'll need when using Terraform on a continuous integration service like GitHub Actions. Terraform offers a few different backends out of the box. For this example, I'm going with the S3 backend, which stores state in an Amazon S3 bucket and also gives the option to lock the state using DynamoDB to prevent it from being overwritten while another operation is in progress. To define the S3 backend in Terraform, the only thing needed is to specify the backend block inside of the top level Terraform section in the main.tf file with the name of the backend, which is S3. This block accepts a few configuration settings like setting the keys to access the S3 bucket, the bucket name, the name of the state file, and more. For this example, I'll configure the backend through the GitHub Actions workflow using a combination of environment variables and generating a configuration file, so I can leave this block empty here. One important thing about the S3 backend is that it requires AWS IAM permissions for reading from and writing to the S3 bucket that will hold the Terraform state. If using the optional state logging functionality, as I'll do in this example, it also needs some access to the DynamoDB table that tracks any ongoing Terraform operations. I won't go through the process here for setting up these permissions, but check out the S3 backend documentation on Terraform's website for details on the IAM permissions needed. The Terraform project is now fully set up to provision a new server and save its state remotely, so let's create a GitHub Actions workflow to begin testing it out. In this example, I'll create two separate workflows, one to provision and deploy the infrastructure when opening or updating a pull request, and one to tear down the infrastructure when closing the pull request. I can set up both of these workflows in a single file and use conditional statements based on the event, but I'll keep them in separate workflows to simplify the explanation for this video. For the first workflow, I'll create a new file under the GitHub Workflows directory in my repo called review app deploy.yaml. And you can name this file anything you want as long as it's a YAML file under the .github/workflows directory. This workflow will eventually contain the complete process of creating a new server and using Kamal to deploy the Rails application to the server. In this video, I'll only cover the provisioning steps. I'll start this workflow with the name key to set up a descriptive name for the workflow. I'll use review app deployment as the name for this workflow. This key is optional, but it's a good practice to have a clear description of the workflow for debugging issues and for referring to this workflow if you want to use it for other ones in your project. Next, I'll set up the on key to specify which events we want to trigger this workflow on GitHub. As I mentioned, I want to trigger this workflow when opening or updating a pull request, so we can accomplish that by setting the pull request event type here, and underneath specifying the types of activities to kick off the process as a list below. I'll add 3 activities here. The opened activity checks when someone opens a pull request. The reopened activity happens when reopening a previously closed pull request. And the synchronize activity occurs whenever someone updates the base branch for the pull request. These 3 activities will take care of provisioning the server and deploying the application for testing. Each workflow requires one or more jobs, which defines what we want to execute on GitHub Actions. The first key under jobs is the ID to use, which I'll set to provision. Under the ID, I'll configure the runs on setting to use the GitHub hosted runner for the latest version of Ubuntu, which is called Ubuntu Latest to run the steps I'll define later in this workflow. Another bit of configuration I want to do for this job is to set a few defaults for each run step I'll define later, so I don't have to repeat a few commands for each of those. My Terraform script is located in the infrastructure directory in the repo, and I'll want to execute any Terraform commands while being in this directory instead of the root of the repository. So instead of defining it in every individual step, I can use this section to apply the settings under here for all of the run commands that I have in this job. I can set the working directory for these steps using the working directory key and setting its value to /infrastructure, meaning that all our commands will be done in this directory at the root of the checked out code for our repo. Before setting up the steps for the provisioning job, I'll need to define a few environment variables for Terraform using env. Most of the values for these environment variables are going to be set as secrets in the GitHub repository since I don't want to expose any sensitive information. I already have the secrets I need set up in my repo, so I won't show how to add them here, but if you're new to GitHub Actions, check out their documentation to learn how to use secrets in the workflows so you can apply it to your repository. I'll start by defining the hcloud token environment variable. And as I mentioned earlier, the Hetzner Cloud Terraform provider checks for the API token in this environment variable if it's not set in the script, which is our case here. So I'll grab the value from the repository secrets using the $ and the double curly braces, and using the secrets context and the name of the variable that I set in my secrets configuration, which is the same name, hcloud token. I'll also set the AWS access key ID and the AWS secret access key variables, both using secrets of the same name. So that'll be secrets.aws access key ID and secrets.aws secret access key. These are the keys that the S3 backend needs to authenticate the IAM user that can access the S3 bucket to save the Terraform state, and the DynamoDB table for the optional state locking. The last variable I'll set here is the tf_var underscore server name variable, which looks a little bit funky with the upper and lower case mixed in, but it is necessary for this example. My Terraform script requires the server name variable to provision the server's name, and Terraform allows us to set these values through environment variables by appending the variable name with tf_var as shown here before the actual variable name. For the value, I'll use team yap review. And since the server name has to be unique across a Hetzner Cloud project, I'll use the pull request number taken from the GitHub context. So I'll open the $ curly braces and use the GitHub context. And I can grab the details of a pull request using event.pull request. And I can access the actual pull request number with number. In this example, if the pull request that triggers this workflow is pull request number 1, then the server name is going to be called teamyapreview1, which will ensure uniqueness across all pull requests in a repo. With all of the jobs set up out of the way, I can finally begin defining the steps for this job. This job is going to contain 6 steps. First, I'll check out the code from my repo into the runner. So for the first step, I'll give it a name of checkout repository, and I'll set up an action with the uses key and specify the action/checkout action, which comes from GitHub. And I'll also make sure that it uses the latest major version, which I can define after the @ symbol, and the latest version is version 4. The next step is to set up Terraform in the runner. I'll call this step setup Terraform, and I'll use the official HashiCorp/setup Terraform action with the latest version, which is version 3, to ensure that I have the latest version of Terraform's command line interface installed. I also want to lock this down to the latest stable version using the with argument, and then setting the Terraform version option here to the version that I want to lock down here, which is 1.10.3. Next, I'll dynamically generate a configuration file to set up the S3 backend for Terraform. I'll call this step create backend configuration, and I'll run a multi-line command starting with a pipe to generate a new file. For the command, I'll use Linux's built-in cat command and read the contents defined below using a here doc with the EOF marker and closing it at the end. And I'll redirect the output of the content in between this here doc using a right angle bracket to a file called backend.conf. And in between the here doc markers, I can begin setting up the contents of this file. So the backend configuration uses key value pairs to set up the backend setting where each value is a string. The first key to configure is the bucket, which is the name of the S3 bucket where the Terraform state is going to be stored. For this example, I'll use a bucket I have in my account called Denmark Terraform. The next key I'll use is the region, which is where the bucket and the DynamoDB table are going to be located. So in my case, it's going to be located in the AP Northeast 1 region. Next is the key setting, which is the name of the object to create in the Amazon S3 bucket that will contain the contents of our Terraform state. I want this value to be unique, so I'll store the state in a folder called Team Yap Review. And again, I want to use the pull request number as I did earlier. So I'll use the GitHub context with the event pull request and get the number of the pull request. So we have a unique directory for each pull request that'll use these remote states. Inside of the folder, I'll call the state terraform.tf state, which is the convention to use for these state files. I'll also want to set up the optional state locking so that if multiple events trigger this workflow, like for example, multiple commits happening in the same pull request branch, we can make sure that it'll only handle one state operation at a time to keep the state consistent. This is set up in the S3 backend with the use lock file option and setting its value to true. I'll also need to specify which DynamoDB table to use to keep track of the locks. The S3 backend requires a DynamoDB table with a string type partition key called lock ID located in the same region that I defined in this configuration. So I'll need to set the DynamoDB table setting here and using a name of a table I set up already for this, which is called Denmark Terraform state. After setting up the configuration file, I'll add a new step to initialize the Terraform project called Terraform init and running the Terraform init command with the backend config option pointing to the file created in the previous step, which I called backend.conf. So this will make sure that the project has the Hetzner Cloud provider and the S3 backend pulled in, and it'll configure the backend with our settings across all workflow runs. The next step I'll do after initializing the Terraform project is called Terraform validate, and I'll just simply run the Terraform validate command to make sure that if I made a mistake with the syntax, it'll fail quickly before attempting to provision the infrastructure. Finally, I've reached the fun part, which is where the review app server is provisioned automatically. I'll create one more step here and call it Terraform apply, and I'll run the Terraform apply command with the auto approve option to apply these changes on Hetzner Cloud and approve it automatically since we can approve it ourselves through GitHub Actions. The provisioning workflow is now fully set up, so let's get to the teardown workflow when closing a pull request. I'll create a new file under the .github/workflows directory called review app teardown.yaml. And I'll copy the exact workflow that we have here and paste it to the new one, making a few minor revisions along the way. So I'll update the name of the workflow to review app teardown to better reflect what it does. I'll also update the different types of activities that'll trigger this workflow. So I'll clear all the existing ones and I'll add a single one called closed, which handles the scenario when someone closes an existing pull request, whether by merging the branch or closing it without a merge. Finally, at the end, I'll replace this Terraform apply step with Terraform destroy and change the Terraform apply command to Terraform destroy, keeping the auto approve options to perform the step automatically. The rest of this workflow will remain the same since we'll still need the same configuration to set up Terraform and to access the state on Amazon S3 and DynamoDB. One last thing I'll need to do is to update my .gitignore file for the repo to make sure we don't commit any unnecessary files or sensitive data related to Terraform. The easiest way to do this is to go to GitHub's gitignore repository, which contains an extensive collection of templates for all kinds of tools, and copy the contents of the terraform.ignore template to your repo's .gitignore file. So I'll just copy everything here, and I'll paste it at the end of my existing .gitignore file. I'm doing that just for this example, but as you should always do when taking anything from the internet, make sure to review whatever you copy into your codebase beforehand. So let's make sure I properly set up these workflows after saving them in my repository. I'll check out a new branch in my repository called review apps. I'll commit all of the changes here with git add, and I'll just commit them using git commit with a message of setup, server, provisioning, and teardown. And I'll push the commit to GitHub using git push origin and the name of the branch, which is review apps. And GitHub will give me the link to open the pull request, so I'll do that here. I'll keep the default title based on the commit message, and I'll add a quick description for testing. So when I open the pull request, I'll go to the Actions tab in my repository, and I should see a new workflow run triggered by the opened activity that I set up in the provisioning and deployment workflow. If I set everything up correctly, the workflow will run through each step to provision the new server and pass successfully. If you're following along and something fails in this step, it's usually because the secrets used in the GitHub Actions workflow aren't set up in the repository correctly, or the IAM user authenticated using the access keys set up in the workflow don't have the right permissions to access the S3 bucket or the DynamoDB table configured for the S3 backend. So make sure you have all the secrets set up correctly and test the Terraform setup manually as I did earlier in the video to help debug the issue. With the provisioning workflow validated, I'll close this pull request, which should trigger the closed activity and run the teardown workflow. Again, if everything works, the workflow will delete the server from Hetzner Cloud and finish its run successfully. This video sets up the foundation for creating a review app system when using Kamal to deploy your web applications. I covered how to use GitHub Actions to run a Terraform script that automatically provisions new servers on Hetzner Cloud that we can use to deploy a web application for testing. While the example here uses tools like Terraform, Hetzner Cloud, and GitHub Actions, you can use these same concepts to work with your preferred tools and services, whether it's OpenTofu instead of Terraform, DigitalOcean instead of Hetzner Cloud, or GitLab instead of GitHub. In the next video, I'll expand on the GitHub Actions workflow I created to set up Kamal for deploying your application to the server provisioned by opening a pull request. This step will handle configuring GitHub Actions to allow access for deploying your server, along with an easy way of setting up DNS records to easily access the application for testing, so stay tuned for that. As always, if you found this video helpful, consider subscribing to this channel for more tips on helping developers ship their code confidently, from development to deployment. You can also check my website for more in-depth articles covering Rails, testing, DevOps, and other software engineering topics. Thanks for watching, and I'll see you in the next video.